Hello, my name is Hunter Levinson, and this is my Physics 2212 lab report on the microscopic view of DC and RC circuits. The purpose of this lab was to make predictions of the properties of a circuit through key physics principles with the conservation of energy and current in both simple series and RC circuits. We also had to predict the behavior of circuits containing resistors in series and circuits containing ohmic resistors and capacitors. We then had to compare these predictions to the actual values recorded by a multimeter. The key concepts we had to use for this lab were Ohm's law, showing the relationship that voltage is equal to current times resistance, the loop rule, stating that the total net voltage of all the components of a loop of an electrical circuit will sum to zero, and the node rule, stating that the current entering one node will be equal to the current leaving that same node. Since this is a circuit in series, we know that all the currents going into each node will be equal to each other. The key formulas, as shown above, we have Ohm's law, which is the top two equations. And then Ohm's law is the second equation. The top equation is the equation for capacitance. And then the third equation is the loop rule. And the fourth one shows the relationship between the charge of a node over time. Our final results show that the two resistors, as you'll see in the next slide, had the same current going in as we talked about just now, had slightly different resistance values of 48.73 and 102.03 as we were initially given, and a slightly different net voltage as well. To calculate the predicted current going into this system that we created above, here is a generalized view of it. We set the EMF equal to the current times the sum of the two resistors, as the current going into both resistors is the same. Thus, the net EMF going from two batteries, both 1.5 volts, is equal to the current times the sum of the two, which is 147 resistance. Our calculations or our predictions show that this should be equal to 0.0204 amps, while the measured current that we got was actually 0.0197 amps. Of course, when we reverse the ammeter, we got the negative of that value. When we switched the ammeter to a voltmeter, we predicted that our current was now going to be zero because the voltmeter has a very, very high resistance that we treated as infinity. And the voltmeter should have been equal to the 3 volts that were being constantly pumped in by the EMF. Our calculations showed that the current was indeed zero and that the voltage was 3.1 volts, likely due to faulty readings or a faulty battery. Our potential difference in nodes, we used the loop rule, once again, and manipulated it to show that the voltage created by the battery should have been equal to the voltage by both resistors. Funnily enough, we got from our calculations with a voltmeter that the voltage from each of the two resistors was actually equal to the current we calculated times the resistance of those resistors, rather than the current that we had recorded from our ammeter. Thankfully, our calculations and recordings matched up with loop rule, showing that the 3.07 volts created by the battery was equal to the sum of the other two voltage nodes. For an ammeter in parallel, when we put the ammeter around both sides of the 100 ohm resistor, we realized that energy takes the path of least resistance. This meant that we could basically disregard the second resistor and just treat the system as though it had one resistor. Recalculating, we got that the current should be 0.0638 amps. Next, we had to use these values from the first 4 parts to find the true resistor values by dividing the voltages that we got by the current. Doing so, we got the values of 48.73 ohms for the first resistor, 102.03 ohms for the second resistor, and then we thought that the wire and ammeter should have 0 ohms if it's an ideal system. For an RC circuit, we had 2 RC batteries, a 1F capacitor, and 2 light bulbs. One was 10 ohms and the other was 20 ohms. We saw that the 10 ohm one had constant brightness at first, but dimmed after about 1 minute and 20 seconds. The second one also had constant brightness and had a 2 minute and 10 second discharge time. These results make sense, as the resistors with lower resistance will allow more current to flow through, thus it will drain the charged capacitor quicker. This phenomenon causes the lower resistant bulb to die quicker. Our sources of error were that the overall battery's resistance and capacitors could break down, leading to varied voltage, resistance, and capacitance, as we talked about earlier. There could have also been human error in time readings, And finally, faulty multimeter technology can cause false readings of amperes and voltage. For a what-if question, the capacitor would likely reach full charge instantly, as there would be no resistance in the wire or capacitor. However, when we performed this experiment, it took roughly 4 seconds to fully charge our capacitor. The reason for this is that there is actually some resistance created by friction in the wire, which we usually do not account for in an ideal circuit model. Thank you very much.